Hello everyone, today we are going to discuss various examples on discrete time Fourier transform. The topic discrete time Fourier transform has also been explained in the previous lecture. So before proceeding to these examples, we must know these three things or the things to remember. First is the discrete time Fourier transform formula. It is given by this formula. And second is IDTFT, inverse discrete time Fourier transform, and it is given by this formula. Second thing, you must know that the discrete time Fourier transform and continuous time Fourier transform, both transforms are continuous in frequency domain, right? And the third thing, that the discrete time Fourier transform is periodic with period 2 pi, while CTFT was not periodic, right? So come to the example number 1. In this example, you have to find the discrete time Fourier transform of the given signal xn a to the power n u of minus n minus 1. So before you find the discrete time Fourier transform of this function, you must know how it will be represented graphically. So here we have represented it graphically. From the graph, we can see that the function is existing from minus infinity to minus 1, right? So put this value in the discrete time Fourier transform formula. We have put this value here and have taken this u of minus n minus 1 to the limit, to the summation, right? In the summation, the limit will be from minus infinity to minus 1, as we can see from the graph also. So the function becomes this, that is summation from minus infinity to minus 1 and this function. Now what we have to do, we have to make it as a GP. For making it as a GP, because in case of GP the summation extends from 0 to infinity, we may have to make this limit positive. So for making the limit positive, you have to just consider that n is replaced by minus n. So when you replace n by minus m, then this limit becomes positive and this minus n becomes positive n, and it becomes this summation n is equals to 1 to infinity 1 upon a e to the power j omega to the power n, right? But here we can see that the limit is from 1 to infinity, but in case of GP the limit is extending from 0 to infinity. So we have to make this limit 0 to infinity. For making 0 to infinity, we have to just add 1 in this expression or subtract 1 in the same expression, right? And solving for that, then we will get this x of e j omega equals to 1 upon a e to the minus j omega minus 1, right? This is the discrete time Fourier transform. Now for this discrete time Fourier transform, you have to draw the magnitude spectrum. How you will draw the magnitude spectrum? You have to just take the magnitude. For the magnitude, what will you do? You will take the square root, and under that square root the real and imaginary parts are separated. We will take the square of the real part plus square of the imaginary part. We can apply that approach to find the magnitude of discrete time Fourier transform. Here we have applied that approach and calculated the magnitude spectrum of DTFT, and this is 1 upon under root 1 minus 2a cos omega plus a square. You can also understand how we have calculated the magnitude spectrum, right? Now come to next slide. In this slide, you have calculated the discrete time Fourier transform of the given signal a to the power minus n u of minus n minus 1. In the previous example, it was a to the power n u of minus n minus 1. Here it is a to the power minus n, and in this the value of a is greater than 1, but here the value of a is less than 1. So you should also have to remember the transforms of these functions, that is xn is equals to a to the minus n u of minus n minus 1 and a to the power n u of minus n minus 1. You have to learn the transform of these functions also, that you have also done in case of continuous time Fourier transform. In that you have made a transform pair table. Similarly, you have to make the transform pair table in the discrete time Fourier transform for some pairs of transforms, right? So now apply the discrete time Fourier transform formula. Here we have applied. In the similar way, we have taken this value of xn here and taking this u of minus n minus 1 to the summation. After taking it to the summation and making it as a GP and solving, we will have x of ej omega is equals to a ej omega upon 1 minus a ej omega. Here we have not calculated the magnitude spectrum, but if you want to calculate the magnitude spectrum, you can go with the same procedure that we have discussed here to calculate the magnitude spectrum, right? Now come to next example. In this example, you have to calculate the discrete time Fourier transform of xn is equals to a to the power mod of n. So before you find the discrete time Fourier transform of this given function, you should know what is mod of n. So mod of n is this. An is defined when n is greater than equal to 0, and it will be a of minus n when n is less than equals to minus 1. So in the formula of discrete time Fourier transform, the limit will break. The limit will break according to this function. For this function, the limit will extend from 0 to infinity, and for this you have already calculated the Fourier transform for this function. Here you have calculated the Fourier transform of this function. So put this value from here. You are putting that value from there to here, right? And an un Fourier transform also has been calculated. It was calculated in the previous lecture. So from that we have also taken that value and putting this value here, and on solving we will have the discrete time Fourier transform x of ej omega equals to 1 minus a square under root 1 minus 2a cos omega plus a square. It itself is a real part. So when you take the magnitude spectrum of this function, it becomes the same function, right? Now come to the next slide. In the next slide, you have to calculate the discrete time Fourier transform of the rectangular pulse. Here you do not have to calculate the discrete time Fourier transform. Here you have to calculate the inverse discrete time Fourier transform, right? Inverse discrete time Fourier transform means the function is given in frequency domain. So first you have to understand this function. As I already told you, the difference between the continuous time Fourier transform and discrete time Fourier transform. The difference was that the discrete time Fourier transform is periodic with period 2 pi. Then how you will draw it graphically, or how you will represent it graphically? So first you represent this function rect omega upon 2 upon omega c in frequency domain. Here if we represent this function in frequency domain, the limit will extend from minus omega c to plus omega c. As it is the discrete time Fourier transform, because it is defined in frequency domain, so how next you will draw? The next, here it is drawn a square wave, and this square wave is repeating after 2 pi interval. Why it is repeating 2 pi interval? Because it is a discrete time Fourier transform. It is given that it is a discrete time Fourier transform, as you have to calculate IDTFT of this function. So it means it is a discrete time Fourier transform of some function. So this waveform will repeat after every 2 pi interval. So it will extend up to infinity this side and minus infinity this side. So you have to calculate IDTFT of this function. So take the IDTFT formula from the first or second slide we have written there. From that we have written the formula of IDTFT is there. Now write the value of x of ej omega in the interval minus pi to plus pi. In the formula the integration is defined over an interval of 2 pi. So under an interval of 2 pi the limit is extending from minus omega c to plus omega c. By putting this limit from minus omega c to plus omega c and solving this integration, we have sine omega c n upon n pi. And you also know that the sine function can be represented in terms of sinc function. When you represent this function as a sinc function, then we can represent it graphically also. Here we have represented it graphically in the similar way that we use to represent the sinc function, right? Now come to the next example. In this example, you have to calculate the inverse DTFT, right? Inverse DTFT means it is given in the frequency domain. In the similar way that we have discussed here to represent this function, we are using the same procedure to represent this function graphically. How we will represent it? Delta omega. Delta omega in frequency domain, it exists at omega equals to 0, right? Omega equals to 0. The impulse value is, the strength of the impulse is 1, right? But it is DTFT of some function. So DTFT, if it is a DTFT of some function, then this value repeat after every 2 pi interval. So we have repeated the same waveform after every 2 pi period, and it is extending from it is extending towards plus infinity in this side and minus infinity this side over an interval of 2 pi, right? So you have to calculate the IDTFT of this function. We have taken the formula, putting this value in this formula, delta omega value of integration is from minus pi to plus pi. It is given in the formula. So minus pi to plus pi, it is delta omega. Apply the impulse property. By applying impulse property and solving the integration, we have 1 upon 2 pi, right? So the DTFT of delta omega is 1 upon 2 pi. We can write the discrete time Fourier transform of delta omega is 1 upon 2 pi, or we can represent this function as this also, delta omega minus 2 pi m, as it is extending from minus infinity to plus infinity and repeating over an interval of 2 pi. So this representation can be done, or it could be written mathematically as this function, right? So the Fourier transform of inverse DTFT of this delta omega is 1 upon 2 pi, right? So here we have discussed these examples. On this basis, we will give you some assignments, right? So thank you very much.